thank you everyone for coming, and thank you also to the organizers for the so far very nice conference. And thank you, Moritz, for a very good introduction to the free energy principle. I can already skip quite some things to get quite to the more nice results, so that it's really nice. Yeah, my talk is about perception as inference, which is very much related to the generative models Moritz was talking about before. So in my talk, I won't talk about the scientific models, but only about the generative models, just as some kind of warning or some kind of heads up. Yeah, the goal of my talk is actually twofold. So I've been studying this topic for the past year or something, reading papers, and there are some points when I was reading papers which I think are very much underemphasized. So that's the first part of the talk. I want to say a little bit more about generative models and about the things that I think are very important to realize about these. And then the second part of the talk will be, I will be comparing two types of inference strategies one can use for generative models, which are amortized inference and yeah, something I am in this talk calling predictive coding, but I think maybe you are referring to this more as predictive processing, so the terminology differs a little bit, or is a bit different within the literature, but I will try to make it more clear as soon as we get there. So, since this is a conference on consciousness and my talk is more on perception, I thought it was good to devote at least one slide on how I think they relate. So I'm a big fan of philosopher and neuroscientist Sam Harris, and he describes consciousness as the space in which experiences can arise. So if we see this cloud as our consciousness, as this space, and then we have experience, which is some kind of an element in this space, and what I'm saying, perception influences what kind of experiences we have. So what are the contents of our consciousness, and yeah, that's what I want to say about it so far. And then a little bit more about perception. So I would say perception is some kind of process from converting sensory input. So that's what I call X here. So you get some kind of signal from the outside. And then we want to make so this is also already a loaded word, a representation, an internal representation of the sensory input. And I'm very curious maybe in the discussion session to see if your view of representations is the same as mine or not. And yeah, so basically we try to find some kind of, yeah, so we could call this a representation, or we could also call it a cause. So what I'm trying to say is what the brain is trying to do is it's trying to somehow find a cause for what is causing the sensory input it is receiving. And this cause is basically unobserved, and that's why I'm calling it a latent cause. So it's more like a best guess, so to say. Yeah, so Moritz already talked about generative modeling. I just wanted to devote this one slide to explain that a little bit more. So if we look here, we want actually to go from sensory input to latent causes, right? That's what perception is. And then the most direct way to do that is to make a model of that, to go from X to Z. And this is actually a very kind of broad distinction within machine learning, so not even only cognitive science, but machine learning in general, that one can then model this process straight away, which is called discriminative modeling. But what one can also do is actually make a generative model out of it. So we have a model from Z to X, And then, so from the latent causes to the concrete sensory input. And then we want somehow to perform inference on this model. So we are modeling, the model in our brain, so to say, is a model from Z to X. And then we have to perform somehow inference on that model. And the two strategies how to do that, those I will talk about more in the second half of the talk. So, but this whole talk will only involve generative modeling, so models from Z to X, and I won't use any discriminative models. Yeah, one other distinction I would like to make, which this is one of the things I sometimes think is underemphasized, is that a generative model is just a model that is in our brains. So that is most likely a very simplified model of the actual process that is happening to generate the sensory input we are receiving. So the generative model is a model in our brain that is like saying, okay, this internal representations of things, or like these internal causes cause the sensory input, but then there's actually a real generative process which is happening outside of us, which is going from the real causes to sensory input. But what we have in our brain is the generative model, which is some kind of simplified version of an actual generative process. Yeah, this theory of generative models started already quite long ago with Helmholtz, and he made some kind of model for this, specifically for visual input and what is happening, for example, when you move your head, and that you can then make distinctions between. So when I move my head, I get different visual input, but that's only because I'm moving my head, nothing about the external world that is changing. So, and then a generative model actually can help by making a distinction, okay, what causes the change in sensory input, either my own movements or because actually something externally is changing. And then later on, generative models, this is not an exhaustive list, but later on, generative models also are used in predictive coding, theory of the Bayesian brain, and the free energy principle of, so basically perception according to free energy principle. And then in this talk, what I want to focus on is how is this generative model learned, and how can one perform inference on this generative model. Sorry, what time did I start? Do you know that?
More than 60 minutes.
60 minutes. That is including the questions. But then I'm going a little bit fast. So some quick examples of these, to get a bit clear idea what is the latent cause and what's the specific sensory input. So for example, if we look at this picture, this is a concrete sensory input we can receive. But then what the brain is trying to do is trying to see what caused this sensory input. And then we would say probably, okay, that's a white square stacked on 4 black circles. And so to make a brief distinction, so this is how we understand what we see, and this is just like only a concrete visual input. And same for this one. So if we see this, then what our brain is trying to do is trying to guess, okay, what caused this sensory input? And then we would probably say, okay, that's Michael Jackson standing in front of a light. And what's then funny is that, so I was talking before about that the generative process is something different from the generative model. And in this case, we see that the generative process is actually some kind of weird sculpture that is causing this shadow. But our brain will just think, okay, it was Michael Jackson. So then these two models don't always have to agree. Yeah, and now one thing I was wondering myself always is how does the brain actually learn such a generative model, and how does it learn these representations? And one thing I like when I was before reading about this topic, I was like, to me it always seemed okay. What the brain is trying to do is trying to match the sensory input to some kind of pre-existing latent cause that's already in the brain. But then the question is, how do those representations, where do they come from to begin with? And then what I did together with a colleague of mine is just make a very, very simple example of a generative model. So what we have here, our latent cause is just one number between minus infinity to infinity. And then we have some kind of function. And then the output of the generative model is a picture, like, I don't know, 24 by 24 pixels or something. And so if we start just with a random initialization of this model, one extra remark. So, and what I'm trying to model here is, so we pretend that there's a baby in a world, and that in this world there's the only thing the baby sees is handwritten ones and handwritten twos. And then we are trying to see what is happening with the generative model of this baby. So in the beginning, before it has learned anything, we can put like an input of Z in this model and then see what the generative model, what the sensory input, basically what the X is that comes out of the model. And we see that that's just random noise. But then, after we are training this generative model, we actually see that if we then put different numbers, different sets into the model, we actually see that it is learning to somehow generate the things that it has observed before. So it can generate, this model can generate handwritten ones and handwritten twos. And then in this case, what I found very interesting is what it actually learned to do is to represent the handwritten ones and handwritten twos by using this one variable Z. And then in this case, that was pure coincidence. When Z is smaller than 0, that would correspond, that was the representation, so to say, of a 1. And when Z is bigger than 0, that represents a 2. So this is a little bit to illustrate, to make it a bit more concrete, how does the organism basically learn the representations? And in this case, it learns them by associating this Z to either the 1s or the 2s, depending on the value of the Z. So I can imagine that this is maybe a little bit short, so if you have any questions, please ask them later, because I find it a lot of fun to talk about this a bit longer. So, I think I'm not doing very well on time.
11 minutes.
11 minutes. So, what I will do now is, so now I wanted to go a little bit more into the formal mathematics of the generative model. And what I find personally very interesting is to see how different approaches, so the different approaches that all use generative models, where do they differ, and where do they actually overlap, where are they actually saying the same but maybe in different words. And one thing I noticed is that in the process of learning the generative model, actually all theories somehow say approximately the same thing. So we saw already before, also in Moritz's talk, that the goal, according to the free energy, is to minimize the surprise. So that is what I'm writing here basically. So xi's are data that are coming in, and we are trying to find a model that has a high likelihood basically of putting out the x's that we are also seeing. So for example, before we were seeing the ones and the twos quite a lot, and in the beginning, before the model was trained, it was only putting out noise that didn't look like the one and the twos. But then after it was trained, it had a very high likelihood of putting out a number like that would look similar to either a 1 or a 2. And so that is basically according to free energy principle predictive coding. We are trying to minimize the surprise or maximize the evidence or maximize the log likelihood. That's all the same thing. And then there's another theory by Peter Dayan called the Helmholtz machine, and also later variational autoencoders. They optimize this KL divergence between the real distribution that is in the world and the distribution that the generative model is generating. And then we want to somehow make this distance as small as possible. But when working out the mathematical details, these two objectives actually also are equivalent. So I found that very interesting to realize that actually all approaches that use generative models have the same objective when it comes to learning. And what is very important also to realize is that when we are actually trying to optimize that objective, so when you're doing the derivation, so when we are trying to compute the gradient, what we see is that in this expression of the gradient, we need a term which is called the posterior distribution, which is a distribution of latent causes given the sensory input. So that's the opposite of the generative model. The generative model is saying latent causes and goes down to the sensory input. So sensory input given latent causes. But in actually to perform the learning, we need the posterior distribution. And their theories actually start to diverge. So there are, I would say, two main proposals. One is called amortized inference, and one is called predictive coding or perception according to free energy principle. And I'm going to say quickly something about these two approaches. So the first approach, amortized inference, which is, for example, the Helmholtz machine and variational autoencoder. They use one model to perform the inference, so to get this distribution pz given x. So we have first here the generative model, and then there's some kind of fixed called recognition model with also its own parameters. So in this case the parameters are called phi. And then when we are getting observations, these phi's are slowly being optimized so that we slowly get some kind of distribution which is similar to that posterior distribution pz given x. And yeah, and then if the organism actually wants to perform perception or perform inference on the generative model, it can just do some kind of forward pass through this model because the parameters are then at some point learned, and then it can very easily find the latent cause of the sensory input according to the model. And the big distinction between the other approach to performing this inference is that according to free energy principle or predictive coding, when a sensory input comes in, we find a new set of parameters. So before we were somehow slowly optimizing one set of parameters, but what predictive coding says is that when the sensory input comes in, we completely forget the previous parameters and we are trying to find a new set of parameters to minimize the free energy. So I forgot to say that actually this previous approach is also optimizing a free, that was actually the title of my talk, free energy minimization. So both these approaches minimize the free energy, but here there's a sum because it's gradually being optimized. And here the parameters are optimized individually for every sensory input. So I would say that is the big distinction between these two approaches. And then they both have their, I'm going to skip this for now, they both have their advantages and disadvantages. I would say one big point is actually that in the first approach, inference can be performed very fast because we already have the parameters and we can just do a forward pass. And then with predictive coding, this new set of parameters has to be found for each individual sensory input. And then very recently, people are also suggesting to actually combine these two approaches into some kind of new architecture so that you can take best of both worlds, so to say. Yeah, I think that is not everything I wanted to say, but the main things that fit it in the time that we have. Yeah, I think this is some kind of takeaways. Maybe you can read them whilst there are questions being asked. Thank you very much for your attention.
Thank you very much.